Can start recording, Sandhya.
Yes, I have done.
No. Okay, so we'd like to start hypothesis testing. Hypothesis testing has been done before in this series of lectures, but there are many new members in the group. And we also have a clearer understanding of CLT, central limit theorem, especially its proof. I'll revise this proof today briefly and then move to hypothesis testing. Hypothesis testing is the bread and butter of machine learning. Anywhere we have automation, we have to apply hypothesis testing, especially if the value of the created system is close to the performance of the baseline system. So let's see the how, the idea of central limit theorem and the idea of this standard normal distribution helps in testing if a hypothesis is correct or not. And there is a very systematic way of tackling this question coming from statistics, which is much, much older than machine learning. So now, by way of revising, central limit theorem, you would recall, is that summation of n independent random variables, we may or may not know their distribution, each with mean mu and variance sigma squared. This is given. The summation of these variables is also a random variable, and particularly this follows a normal distribution with mean n mu and variance n sigma square. So we take the summation of mu's, which becomes n mu. This becomes the mean of the new variable, which is summation of n random variables, and its variance is n sigma square. So the standard deviation is sigma root n. So if I subtract the mean from Sn and divide it by the standard deviation, I get a standard normal distribution. The other form is more useful, which is that if we take n independent random variables forming a sample from a population with mean mu and variance sigma square, then the sample mean, okay, not the sum, the sample mean is normally distributed, but with a difference. Its mean is mu, and the standard deviation is sigma by root n. Okay, variance is sigma square by n. So this is the result which we have also proved, but I would like to go over this proof once again, just to make sure that this is well understood. We are helped in the proof by something called the uniqueness theorem. That this theorem is really unique. This says that if x and y are random variables having moment generating functions mxt and myt respectively, then x and y have the same probability distribution if and only if their moment generating functions are identical. So moment generating function, we have spent quite a lot of time in the last lecture giving examples of moment generating function in two cases: the discrete case, throwing of dice, and for standard normal distribution, where the mean is 0 and standard deviation is 1. So moment generating functions being equal makes the distribution equal, and vice versa. Distribution being equal makes the moment generating function equal. So moment generating function and the probability distribution function are one and the same, okay, for all practical purposes. So now what we do is that we look at the usefulness of uniqueness theorem in the proof of the central limit theorem. Okay, so it always helps to look at the form of the distribution repeatedly. So normal distribution, we know this is e to the power minus y minus sigma square by 2 sigma divided by sigma root 2 pi. This is the normal distribution form. And for standard normal distribution, sigma is 1, mu is 0. So we have this e to the power minus y squared by 2, 1 by root 2 pi. And from this form, we have been able to generate the moment generating function. Moment generating function is e to the power ty into the probability distribution of y. In case of continuous distribution, we have to take the integral from minus infinity to plus infinity. This is the moment generating function for standard normal distribution. So let us remember this point again and again, that we have to take the random variable, multiply it by t is the controlling parameter, raise it to the power of e, multiply by the probability density function in case of continuous distribution, and dy, and integration going from minus infinity to plus infinity. So we were able to show that the moment generating function of standard normal distribution is e to the power t squared by 2. So then we constructed the proof with the procedure that we show the moment generating function for Sn, which is the summation of these n random variables, is same as the moment generating function of the standard normal form. And Sn star is Sn minus n mu by sigma root n. Okay, so all we are doing is subtracting the mu and dividing it by the standard deviation. We have to show that this is standard normal. And to do so, we have to show that the moment generating function of this is e to the power t squared by 2 as n tends to infinity. This is the goal. So we started with the moment generating function form, which is the proof. So you have to take the expectation of e to the power t Sn star. Now, moment generating function is defined as e to the power t into that random variable and expectation thereof. The multiplication by probability density function or probability mass function and taking summation or taking integration is equivalent to taking the expectation of e to the power t multiplied by the random variable. So given a random variable, we can always compute its expectation. Given a random variable, we can also compute the expectation of e to the power t into that random variable. So if you recall, the proof went as follows. We'll just look at the steps once again. Expectation of e to the power t Sn minus n mu divided by sigma root n. Okay, this is as per the definition of Sn star. Now Sn star is xi minus n mu divided by sigma root n. Okay, and n goes from 1 to n. N goes from 1 to n because we have n random variables and they are identically, no, their mean and standard deviation are same. Okay, mean and standard deviation are same. So now I can take this as e to the power I equal to 1 to n t xi minus mu sigma root n, where this sigma is now not only over xi, but it is over mu also, because sigma I equal to 1 to n mu gives me n mu. Now, these are xi, x1 up to xn minus mu, each of them, multiplied by t. T is same, mu is same, sigma root n is also same. Xi only differs, x1, x2, x3 up to xn. So I can take this summation and convert it into a product. Okay, e to the power a plus b is e to the power a into e to the power b. So I equal to 1 to n e to the power t xi minus mu sigma root n. Okay. So now expectation distributes over product, provided the random variables inside the product are independent. So we have already said that xi's are independent of each other. X1, x2 up to xn are independent of each other. So this means I can write this as I equal to 1 to n expectation of 2 to the power xi minus mu divided by sigma root n. And now I can take any xi, and raise it to the power n. Raise e to the power expectation of e to the power this quantity to the power n. Why so? Okay, why so? So, can anybody think of this? How can I raise this to the power n? It is as if we are multiplying equal quantities n times. Not as if we are actually multiplying equal quantities n times. Why is this so? Anybody? Okay. So whatever be the value of I, hmm, let me take x1. Expectation of e to the power t x1 minus mu divided by sigma root n. Okay. Expectation of this particular quantity will be nothing but the nothing but this value, this value as xi takes different values. X1 is a random variable. So we have to take different random variables of x1 itself. So the different values of x1 will be plugged here, multiplied by the probability of that particular value. Okay. So suppose we are talking about discrete distribution. So if x1 takes, let's say, 100 values, then all these values of x1 will be taken, plugged in here, and probability of that quantity will be taken. Now, you will be able to show whether you are dealing with x1, x2, x3, or xn. All these expectation values will come out to be same because their mean is mu and the standard deviation is sigma. So just try to show that expectation of e to the power t into x1 minus mu divided by sigma root n is equal to expectation of e to the power t x2 minus mu divided by sigma root n. Just try to show that from first principles by invoking the definition of expectation. If definition of expectation will be product of this quantity where xi takes a particular value from its own set of values and the probability of that value. And this will come out to be equal to, all of them will come out to be equal because all of them have mean mu and standard deviation sigma. So think about it. It will follow from the definition of expectation. So this is the most crucial step in the proof, which requires the property of expectation to be applied. Now, and it doesn't matter which xi we deal with. So now we discuss this quantity, expectation of e to the power txi minus mu divided by sigma root n to the power n. So now e to the power txi minus mu divided by sigma root n can be Taylor series expanded. And we get 1 plus t into xi minus mu divided by sigma root n plus t square xi minus mu square by 2 sigma square n and so on. Okay. So if we do so, then I think we need a 2 here, 2 here. Okay, so if we do so, Then we come to E expectation of 1 plus expectation of t into expectation of xi minus mu sigma root n plus t square into expectation of xi minus mu square divided by sigma 2 square 2 sigma square n and so on. So expectation of 1, which is a constant, is 1. Expectation of xi minus mu is 0. So this is 0. Expectation of xi minus mu square by definition is sigma square, variance. So 1 plus 0 plus t square by 2n and so on. So we come to the conclusion that e to the expectation of e to the power t Sn star, that is the moment generating function of Sn star, is 1 plus t square by 2n plus other quantities with higher powers of n in the denominator. Now, if we, and everything raised to the power n. Now, if we take the look up in the quantity as Ln as n tends to infinity, then log Ln is n log 1 plus t square by 2n. Okay, so let us get used to the language of mathematics. Instead of speaking in English, I'm speaking in symbols and operators. Okay, so you're just using a different language. Mathematics is a different language. So this is equal to log of 1 plus t square by 2n plus etc. divided by 1 by n. These two expressions are equivalent. Now as n tends to 0, the numerator tends to log 1, which is 0. Sorry, as n tends to infinity, then the numerator tends to log 1, which is 0. Other quantities in the summation, they approach 0. Denominator also tends to 0. So now we can take derivative of numerator and denominator by applying L'Hopital rule. So numerator becomes minus t square by 2n square divided by 1 plus t square by 2n plus etc. And the denominator becomes 1 minus 1 by n square. Now minus 1 by n square cancels here, and numerator becomes t square by 2. Denominator is 1 plus t square by 2n etc. Now as n tends to infinity, this quantity tends to t square by 2. And this you can see is a beautiful proof, right? This is a beautiful proof which used the power of mathematics in the form of Taylor series expansion, L'Hopital rule, and then asking n to approach infinity. So central limit theorem holds for large value of n, and empirically n is taken as 30 or more. So all you have done is that we have shown that Sn star, which is the summation of n random variables, we do not know their distribution, but we know that their mean and standard deviation are identical. We have shown that this follows a normal distribution. Okay, so we made use of uniqueness theorem. So this is very nice. Now let me leave you with one or two questions. First question is, what if these random variables do not have identical mu and standard deviation? What can we say in that case? So do some research, look at some statistics literature and see if you can find the answer to that question. Second question is, if we had to prove the other version of the central limit theorem, that is the mean of the sample follows a normal distribution as n becomes large. Okay, so I take a sample, its size is n. I take many samples, one after the other, and take their means. These means will follow a normal distribution with mean mu, where mu is the population mean, and standard deviation is sigma by root n. Okay, suppose we had to prove this statement. We already know that this statement and the summation statement are identical, are equivalent. But if the starting point was this, can we do the proof? Now, we are saying that this particular statement of central limit theorem, where the mean follows a normal distribution with the mean population, the mean of the mean is the population mean, and the standard deviation is population standard deviation divided by root n. Okay, that's a much more intuitive form. And we can relate to it in many NLP applications. So we had mentioned this point. Suppose I have built a pause tagger, and the language is really potentially infinite. So I have built a pause tagger, let's say for any language, let's say English. Now I take a sample size more than 30 words. I take a sample of, let's say, 1,000 words. Do the part of speech tagging and compute the precision. How many pause tags are correct out of all the pause tagged words? So suppose 800 are correct. So 80% is the precision for that sample. So this way, for different samples, I'll get different precision values. Now I ask you a question. The central limit theorem is for the average, for the mean of the sample. Now the precision that I have computed is, how does it relate to the average value of some parameter of this sample? Okay, the precision is the precision coming from the sample. Can I call it an average precision? Think about this. Okay, now I change the sample, take another 1,000 words, and obtain the precision. So one thing is certain, because of the law of large numbers, that if I go on taking samples and running the part of speech tagger on them, and if I see a trend in the value, okay, mark this carefully. If I see a trend in the value, I can trust that trend. I mean, based on the trend, I can say that the part of speech tagger has average accuracy. Part of speech tagger has an accuracy of 95%. Because I observed 94%, then 93.34%, then 95%, 94.89, 95.87, 96%, and so on. So I'm developing a feeling that the part of speech tagging accuracy is around 95. And this statement will be correct. Okay, this statement will be correct. If I take enough number of samples and each sample is of sufficiently large size, sufficiently large according to central limit theorem means greater than or equal to 30, then this claim will be all right. So I hope you are appreciating this tremendous point here, which we take for granted. Okay. So we have taken, let's say, 25, 30 samples, each sample of size 1,000 words, run part of speech tagger, computed the precision in each sample separately. And if I observe a trend, I trust that trend. Okay. This is a tremendous uh, mm, stand because of law of large numbers. Now it is law of large numbers. So the point still remains. Just 1 minute. The point still remains is that the precision values are not really average values of anything. And the central limit theorem is in terms of the distribution of the mean. So how to reconcile these two facts? Please think about it. Am I audible so far? My screen is visible?
Yes, sir.
Yes, sir.
Okay, so now um, we have about half an hour at our disposal. So let's move to testing of hypothesis and start with some terminology. We'll develop this further with a lot of precision and a lot of elaboration. We did it once in this particular group itself, but every time if we repeat this, the result is likely to be better than what was done before. So two very critical terms in hypothesis testing are null and alternative hypothesis. So there are symbols for this. H0, this is called null hypothesis. And this hypothesis we want to reject. Okay. So this is the strange and the curious part of hypothesis testing. We create a hypothesis with the explicit aim of destroying it. Hmm? So this is a very ironical situation, right? We create a hypothesis and we want to destroy this creation. Okay. So that's a very strange position to take. So H0 is called the null hypothesis, the hypothesis we want to reject. HA or H1 is called the alternative hypothesis, which is the opposite of H0. Okay. And we use the sample statistics trying to reject H0. So sample statistics means the data that we have observed. Now part of speech tagging has been done. I'm getting a feeling that the average accuracy is 95%, but the team that I'm leading, the team claims that the accuracy is 98%. I would like to reject that hypothesis. Okay, that hypothesis I would like to reject. And the opposite of the null hypothesis is called the alternative hypothesis. So we have a specific situation. This was discussed last year also. An empty system is tested as follows. So we have taken 9 test corpora. And here we are allowed to make use of average. The blue scores, average blue scores are 5, 8.5, 12, 15, 7, 9, 7.5, 6.5, and 10.5. So we have taken output of the machine translation system and the reference translations. Now machine translation system will output given any input. Okay, and potentially again we have an infinite set of translations because the inputs themselves can be infinite. However, we take, let's say, 100 sentences in each sample, and for each sentence, we obtain the machine output and compare with reference translation. And as you know, the blue score is always computed against reference translation over the whole test corpus. So now the test corpus is 100 sentences. We get the blue scores. In 9 cases, we have found the blue scores to be these values: 5, 8.5, 12, 5, 15, 7, 9, 7.5, 6.5, 10.5. So do we observe a trend? Unfortunately not. Okay. We do not seem to find a trend here. We can't say that blue score is, I think, 10. And can't say maybe. Of course, you can take the average of these blue scores and say that that average is my blue score. But that will not be completely correct. Okay. Why not? We have to see. But surely from these values, I am getting a feeling that if somebody claims the blue score of the machine translation model, okay, to be 15 or 20 or 30, I will not trust him. The numbers sort of do not support that intuition. How to scientifically address this particular situation? Now, suppose somehow I know that the variance is 4 and I'm able to compute the sample mean, which is 9. Okay. So sample mean is summation of all these values divided by 9. This comes out to be 9. And somehow, this is a very, very hypothetical situation. We know the population variance to be 4, okay, of blue scores. Now, if the company claims blue score is 15, then my null hypothesis is blue score is greater than or equal to 15. The alternative hypothesis is the blue score is less than 15. So this is called one-sided hypothesis testing. I will be worried or I'll be defensive uh, to buy this machine translation tool based on the claim of the company that the blue score is at least 15. This I do not trust really. And the average of the sample has come out to be 9. Okay. So since you can say that since the average is 9 and the claim is 15, I reject it. That's not a very principled way of doing hypothesis testing. Can we just make use of average and say whether the hypothesis is to be rejected or accepted? All right, let us see how to do this more systematically. So associated with this notion is what is called type 1 error and type 2 error. Type 1 is do not reject when in fact should have been rejected. This is called the false positive. So not rejecting means we are accepting. And this acceptance is false acceptance. So this is a case of false positive. Type 2 error is reject when in fact should not have been rejected. This is the false negative case. This is called type 2 error. Okay. Let us remember these all these 4 definitions: null hypothesis, alternative hypothesis, type 1 error, and type 2 error. Okay. Today we'll mainly introduce terminology. Now, more on H naught, the null hypothesis. The data would be unlikely to occur if the null hypothesis were true. Okay. So, in the logical form, null hypothesis implies not data, where NH is the proposition, null hypothesis is true, and D is the proposition, data occurs. So this slide is again very important. Okay, it is based on both logic and statistics and probability. So we are saying that if the null hypothesis which we want to reject is true, it is impossible that the observation that is in front of me would have occurred. Okay, in other words, for this particular problem, if the null hypothesis cannot be rejected, that the blue score is greater than or equal to 15, if the blue score is indeed greater than or equal to 15, then it is impossible that these numbers will come in front of me. Maybe sometimes I'll get a value of 16, sometimes I'll get a value of 5, and so on. But if the null hypothesis is true that the blue score is greater than or equal to 15, these numbers, all of them together, is impossible. Okay? So that is the that is the purpose of null hypothesis. Null hypothesis makes the data or the observation improbable. Now here comes the punchline. If the data is in front of me, then I have got a segment of reality in front of me. I cannot deny reality. So if I cannot deny reality, if I cannot reject reality, which is the data in front of me, then I have to reject the null hypothesis. Because the null hypothesis is a creation based on many factors, maybe bias also. Okay, so that is the point. And if the null hypothesis is true, the observation cannot be true. It is impossible that I'll get these values in front of me. And therefore, I have to reject the data. Now, what is the technique for this? Okay, so these things are very subtle and they take time to internalize and absorb and apply them. We do hypothesis testing very mechanically. Excel sheet uh, comes with a facility of computing test of significance. Okay, there are many tools which do it. But if you are not doing it mechanically, if you want to go to the depth of hypothesis testing, then we have to understand this theory. So any question at this point of time? H0, HA, uh, type 1 error, type 2 error. No? Okay. So let's proceed. So this really relates to maximum likelihood, which is really the pillar of all probabilistic methods, one of the pillars of probabilistic methods. So we move the ball to the court of observations. We formulate H0 in such a way that high probability of H0 makes the data probability low. So the hypothesis and the data are always trying to defeat each other, the null hypothesis and the data. So we formulate the H0 in such a way that high probability of H0 makes the data probability low. So this will be mathematically established. The main point you have to keep in mind now is that the data and the null hypothesis try to upstage each other. Okay, you can look upon this as a kind of wrestling match where H0 is trying to defeat the data, data is trying to defeat H0. So based on the data, we would try to reject null hypothesis. And always remember that null hypothesis has this ironical situation of what is created is attempted to be destroyed immediately. Then there is this notion of p-value, which is also an important quantity. So the p-value or the probability value tells us how likely it is that our data could have occurred under the null hypothesis. The p-value is a proportion. So p-value we have seen many times in the ML papers with a p-value of so and so. That is the how test of significance observations are reported. So p-value of 0.05 means that 5% of the time you would see a test statistic, at least as extreme as the one you found if the null hypothesis was true. Okay, this is fairly technical, and maybe an example will make it clear. Suppose we take a coin and toss it 5 times. So what we have got is HT, HHT. Now there are 3 heads out of 5. So probability of head is 0.6, probability of tail is 0.4. So let me just use the brackets here. Yeah. So probability of H is 0.6, probability is 0.4. Now probability of the observation is what? Probability of the observation is 0.6 to the power 3. Okay, I'm sorry here. 0.6 to the power 3 into 0.4 to the power 2. Okay, and this comes out to be 0.036. So P minus PH, I think this maths has to be properly written. Okay, well, do it next time properly. So this is a way of getting the P value. Okay, so we'll not go to the nitty-gritties now, but just see this point. If we take this probability value as 0.6, okay, then this observation in front of me is likely. There is a high probability that this observation is correct. But on the other hand, if the probability of head is assumed to be, let's say, 0.001, there is no way I can get this observation. Okay? Or the probability of getting this observation is very low. If I toss a coin 5 times, there are there are 2 to the power 5 possibilities of these sequences. Some sequences are very likely, some sequences are not. That depends on the parameter value, which is the probability value of head. So it is the probability value of head which controls how many heads I am likely to see in the sequence. Okay. So now, if I consider the probability of head to be a parameter theta, then theta can take values from 0 to 1. Some values in this spectrum will make the observation which has come in front of me very likely, and some observations, some sequences will not be likely at all. So if I have got an unlikely sequence, okay, which is unlikely for this particular theta, then my hypothesis about theta is to be rejected. Okay, so I understand that this is becoming a bit complicated, but hypothesis testing is a complex subject. Okay, there are many subtle considerations here, so we would like to go slowly, but we would like to master hypothesis testing. Okay, without that, we cannot be machine learning researchers. So now we take another problem, the nicotine problem. This was discussed last time also. And look at some of the claims the company makes. And it is from this classic statistics probability book, Sheldon Ross, 2004. All cigarettes present on the market have an average nicotine content of at least 1.6 milligram per cigarette. This is the population mean. A farm that produces cigarettes claims that it has discovered a new way to cure tobacco leaves that will result in the average nicotine content of a cigarette being less than 1.6 milligram. Okay, so normally you get nicotine content of 1.6 milligram per cigarette. So if the company claims that now the nicotine content is smaller, then we would like to test this claim. So to test this claim, a sample 20 of the farm cigarettes were analyzed. So when this sample size of 20 is taken, we are already bringing in reality. Reality is already descending in front of us. Now, if it is known that the standard deviation of a cigarette's nicotine content is 0.8 mg, this suppose we have got from extensive experimentation. So we've taken cigarette after cigarette after cigarette, recorded their nicotine content, taken average, taken standard deviation, and we've done it for a large number of cigarettes. The standard deviation is coming out to be 0.8 mg. Of course, you can come back and say that if you've taken all these troubles, then why not complete the experiment of finding the average mean nicotine content also, and then see if the average is less than 1.6 or not. This is the most obvious thing, and any of us will suggest this procedure. But that procedure is not well principled. Okay, it is vulnerable. It has chinks in the armor. There are holes in the armor. We need more principle-based approach, and that is what is the purpose of all these discussions. So now, if it is known that the standard deviation of a cigarette's nicotine content is 0.8 mg, what conclusions can be drawn at the 5% level of significance if the average nicotine content of the 20 cigarettes is 1.54? So you see, I've taken the taken a sample of 20 and obtained the average nicotine content is 1.54. Since it is close to 1.6, and less than that, I can believe the company and say that, yeah, I believe you. You have reduced the nicotine content. But that will not be principled. Okay, it's very simple and simplistic also. It is not a correct procedure. So what is the correct procedure? What conclusions can be drawn at 5% level of significance? This is a very important phrase. and the standard deviation of cigarettes nicotine content is 0.8 mg. Many times these kind of sample statistics are obtained from another country or another place where all these experiments, costly experiments have been done. It is costly to get the nicotine content of a cigarette. It needs instrumentation. Now, if somebody else has done it for me in another country, let's say, I take these statistics and use it as a preliminary parameter, although this can be horribly wrong. Um, if the standard deviation is 0.8 mg for India, it may not be the case for Turkey or Hungary or England or USA. May not be. But suppose somebody has done this experiment and I got this value. Then what conclusions can be drawn at the 5% level of significance if the average nicotine content is 1.54 for these 20 cigarettes? So let's see what we do. We first decide age 0. Age 0 is age 0 is the null hypothesis. And the requirement is that the probability of rejecting age 0 when it is true will never exceed alpha. So false negative, okay? False negative, that probability will never exceed alpha. Okay. So now I'll clarify this much better later. We should test age 0, mu greater than or equal to 1.6 versus h1, mu less than 1.6. Okay. So I'm formulating the hypothesis with the goal of rejecting it. And I'll have to see if the data allows me to reject the hypothesis. So proceeding further, the value of the test statistics is x bar minus mu by sigma by root n. This is coming from central limit theorem. So what is this quantity? We know that for large number of samples and each sample of large size, the sample mean will follow a normal distribution. Okay, the sample mean will follow a normal distribution. So so now for the sample which is in front of me, I have got the mean score as 1.54 and 1.6 is told to me as the population mean. Okay, so I compute this quantity. This is called the Z score. Okay, Z score for the observation, and the p value will be equal to probability of Z being less than minus 0.336. Z is normal distribution. This comes out to be 0.368. Okay, now 0.368 is greater than 0.5. So the data does not enable us to reject at a 5% level of significance the hypothesis that mean nicotine content exceeds 1.6. In other words, the evidence through supporting the cigarette, those supporting the cigarette producer's claim is not strong enough to prove the claim. So the result of all that will be that we will not believe the company that he has been able to reduce the nicotine content. Maybe he has been able to reduce, but not that much. Okay, 1.54, which is the claim. Okay, no, 1.54 is the nicotine content, average nicotine content from the sample of cigarettes. 1.54 is less than 1.655, but standard deviation of 0.8 is creating problem. The 5% level of significance is creating the problem. If we are more loose, if we allow 10%, okay, that is more leeway and more flexibility, then maybe we'll be able to accept it. But with these requirement, 5% level of significance, sample size being 20, population being mean being 1.6, and the sample average being 1.4, we are not able to accept the claim of the nicotine company. So let's get this top level view that we are not able to accept this claim. We have to reject this claim. And let's do this in the next class more properly. Okay. Any question before I close? We'll close now. Am I still audible? Screen is still visible?
Yes, sir.
Okay. So there doesn't seem to be any question or comment. I understand that this is not fully clear in the first lecture, but it will become clear and we'll have to do a lot of fine detailed work, okay, with this. Just let me leave you with this particular message, two messages. One, null hypothesis is created with the aim of destroying it. Second, null hypothesis and data fight with each other. Let's see who remains. If data remains, null hypothesis has to go. And if the null hypothesis is there, then the data, there is some inaccuracy with the data. Normally, we do not mistrust the data because it is an observation just in front of us. So we reject the null hypothesis. And the third point is the 5% level of significance, 1%, 10%. What do they mean? Okay, we'll discuss all that. Okay, thank you. We will close the meeting now.